Hi friends, welcome to Brave Solution Times. இன்னைக்கு நம்ம வீடியோல Theorem 1.2 and Theorem 1.3 பார்க்க போறோம். So start பண்ணலாமா? Before getting into the theorem, first I'll explain what is inverse matrices. Let A be a square matrix. So I have already explained what is a square matrix in my previous video, so go check it out. A be a square matrix of order n. So they are given a matrix A of order n if there exists a square matrix B. So they have already said there exists a matrix A, and they have said that if there exists a square matrix, so there will be another matrix B of order n such that so B will be in the form of AB is equal to BA is equal to IN. Okay, so what they are trying to say is ஏன்றது ஒரு மேட்ரிக்ஸ் அண்ட் பின்றது இன்னொரு மேட்ரிக்ஸாக எடுக்கிறாங்க. ஓகேவா? ஸோ இப்போ ஏ அண்ட் பி, ஸோ இந்த மேட்ரிக்ஸையும் நம்ம மல்டிப்ளை பண்ணோன்னா அதே மாதிரி ஏபின்னு பண்ணலாம், இல்லைனா பிஏன்னு பண்ணலாம். அப்படி பண்ணி நமக்கு ஐடென்டிட்டி அப்படின்னு சொல்லி ஆன்சர் கிடச்சிதுன்னா தென் த மேட்ரிக்ஸ் பி இஸ் கால்ட் த இன்வர்ஸ் ஆஃப் ஏ. ஓகேவா? ஸோ இப்போ ரெண்டு மேட்ரிக்ஸ் எடுத்திருக்கோம். அந்த ரெண்டாவது மேட்ரிக்ஸ் ரெண்டையும் மல்டிப்ளை பண்ணும்போது நமக்கு ஐடென்டிட்டி ஃபங்க்ஷன் வந்துச்சுன்னா அப்போ அந்த ரெண்டாவது மேட்ரிக்ஸ் ஒரு தான் இன்வர்ஸ் ஆஃப் ஏ அப்படின்னு சொல்லி சொல்கிறாங்க. ஓகேவா? ஸோ திஸ் இஸ் த டெஃபினிஷன் ஆஃப் இன்வர்ஸ் மேட்ரிசஸ். நவ் லெட்ஸ் கெட் இன்டு த தியரம் 1.2. Theorem 1.2. If a square matrix has an inverse, then it is unique. Okay, which means if a square matrix, which means one square matrix, we are considering it as A, has an inverse, which means for one square matrix there will be only one inverse, then it is unique, right? So first let's write the given part. First they have given a square matrix, so let's take that particular square matrix as A. Let's write let A be the square matrix. Okay, now what they have said, if a square matrix has an inverse, so it has a inverse, right? So let's take that inverse to be B. Let's write let B be the inverse. Okay, so as I said, now you have seen in the definition, right? It's AB. The definition of inverse is AB equal to BA is equal to I, which means we have to multiply these two, square matrix and its inverse. If we multiply that, we must get an identity matrices. So this is called this is the definition of inverse, right? So let's take this as equation 1. Now let's take another inverse. So let us consider another inverse C. So C is another inverse. C be the another inverse of A. Okay, so we are considering that. So by the definition of inverse, what we'll get? A and C, right? So AC is equal to CA is equal to I. Can you understand? ஃபர்ஸ்ட் நம்ம ஒரு ஸ்கொயர் மேட்ரிக்ஸ் கிவன் கொடுத்துருக்காங்க, ஒரு ஸ்கொயர் மேட்ரிக்ஸ் எடுத்திருக்கோம் ஏன்னு, அண்ட் ஒரு இன்வர்ஸும் சொல்லியிருக்காங்க. அதனால இன்வர்ஸையும் நம்ம இன்னொன்று எடுத்திருக்கோம், என்னென்னா பின்னு நம்ம டினோட் பண்ணியிருக்கோம். அதை நம்ம இன்வர்ஸ் டெஃபினிஷன் படி ஏபி அண்ட் இஸ் ஈக்குவல் டு பிஏ இஸ் ஈக்குவல் டு ஐன்னு சொல்லி போட்டுட்டோம். இப்போ நம்ம இன்வர்ஸை பின்னு எடுத்தோம், கரெக்டாக? இப்போ இன்னொரு இன்வர்ஸை நம்ம எடுக்கிறோம், ஏக்கு இன்னொரு இன்வர்ஸ் இருக்குது அப்படின்னு சொல்லி நம்ம எடுக்கிறோம். ஸோ கன்சிடர் பண்ணுறோம். அப்போது இன்னொரு இன்வர்ஸ்னால் நம்ம அதை சின்னு எடுக்கிறோம். அப்போ நம்ம மறுபடியும் இன்வர்ஸோட டெஃபினேஷன் படி ஏசி இஸ் ஈக்குவல் டு சிஏ இஸ் ஈக்குவல் டு ஐ அப்படின்னு சொல்லி டிஃபைன் பண்ணுறோம். ஸோ பை த தியரம் we have to prove that if a square matrix has an inverse, which means for one square matrix there must be only one inverse. If that happens, then it is unique. So you have to you have to prove the uniqueness, right? Uniqueness means for one matrix there will be only one inverse. So we have to prove that, but we have taken two inverse here, right? So what we have to do, if we prove that the both inverse, which means B and C are equal, so that you can say that the particular matrix is unique. So we have to prove B is equal to C, right? To prove B is equal to C, so here B is equal to C. First let's take the left hand side B, right? So here you can see we can write it as bi, because if we consider any number, if we are considering any number and multiplied with 1, then you will get an same answer 2, right? So same goes to an identity element. B into an identity element will again will get an answer b. So I am multiplying I with it. Okay, so b, and here you can see b is nothing but I is nothing but our CA. So let's substitute that there, and now I'm interchanging this since it's in a multiplication. It's okay to interchange it, right? So I'm taking C here and I'm taking this b inside, which means b in the middle, so it doesn't change the value of this. Okay, now you can see that BA is nothing but our I, right? So instead of BA we can substitute I here, so C into I. So therefore for C into C into an identity element, we'll get an answer C, right? So therefore what you have proved, B is equal to C. So B is equal to C. So we have proved this, B is equal to C. So therefore the uniqueness exists. Hence the uniqueness follows. இப்போ next theorem போலாமா? Theorem 1.3. Let A be a square matrix of order n, then A inverse exists if and only if A is non-singular. So what they have given, first they have given a square matrix of order n, and they have given an if and only condition, if and only if condition. So if this condition appears in any one of the theorem, we have to prove this theorem by two parts, which is first part will be, first you have to take this as given. So A inverse exists, you have to take that as a given part. Then what you have to prove is A is a non-singular. So you have to prove first, in the first part you have to take A inverse exists and we have to prove A is non-singular, and in the second part you have to take A is non-singular as an given part, and then you have to prove A inverse exists. Okay, so in the first part you have to take A inverse exists and you have to prove A is non-singular, and then in the second part you have to take A inverse as a non-singular and we have to prove A inverse exists. So this condition only applies if this thing is in a theorem, which is if and only if condition. If this condition appears, you have to prove that theorem in by two ways. Okay, which means by two parts. So these are the parts. Now let's get into the theorem. Proof. As I said, let's take the first part as suppose A inverse exists. So first we are taking this as a given part and we have to prove A is non-singular. So we have to prove, so to prove A is non-singular. So what is a non-singular? If a determinant of A is not equal to 0, then you can say that the A is non-singular. Okay, so we have to show that determinant of A is not equal to 0. So for getting this determinant of A, we are going to use a rule called a product rule for determinants. Therefore by the product rule for determinant, determinant of A into A inverse. So this is the rule. Okay, you have I think you have studied this actually. So determinant of A into A inverse, we can multiply determinant inside, so that you will get determinant of A into determinant of A inverse. Now let's just change the position here, which is we can interchange determinant of A and determinant of A inverse. So we can take that here and determinant of A will go there. So this is nothing but determinant of I, which is our identity element. So we know that our identity element is nothing but 1, right? So therefore determinant of A is not equal to 0, right? We have to prove that determinant of A is not equal to 0. Which means A is non-singular, right? So therefore you can say that determinant of A, which means we can also write it as in this symbol. So this is not equal to 0. So therefore you can say that A is a non-singular Okay, A is non-singular. So therefore you can say that here if A is equal to 0, then the whole term will be 0, right? But here the answer is 1. So that A is not equal to 0. Therefore you can say that A is a non-singular matrix. So we have proved the first part. We have taken A inverse exists as a given part, and we have proved A is a non-singular matrix. Now we have to take A is a non-singular matrix as a given part. Suppose A is a non-singular matrix. Okay, so A is a non-singular. So what we have to prove? We have to prove A inverse exists. Okay, so what is the formula of inverse? Is A into A inverse. So I have already said that our formula for inverse will be AB is equal to BA, which is equal to IA, right? Now let's consider B to be A inverse. Okay, now from now on we are not gonna use B as an inverse. Instead of that, we are gonna use this symbol. Okay, B of A inverse is equal to I. Sorry, I mean A inverse of A is equal to I. So we are gonna use this formula from now on. Given part is A is a non-singular. For proving this, I am going to take a theorem number 1.1. So that by theorem 1.1 we have A into adjoint A is equal to adjoint A into A, which is equal to determinant of A into I. So this is quite similar, right? So that's why I have taken theorem 1. So from this theorem 1 you can see that here there is an I, right? So let's take this as an equation 1. Here there is I, but in this equation we have determinant of determinant of A into I, right? So we have to cancel determinant of A here. So what we are going to do is we are going to divide determinant of A in this whole equation. Okay, so we are going to divide determinant of A, then we'll get A into adjoint A divided by determinant of A, which is equal to adjoint A into A, which is divided by determinant of A, will be equal to I divided by determinant of A divided by determinant of A. It will get cancelled, so that we'll get only I. Okay, now let's write this in a proper manner. So we'll get, let's take A here. So that we'll get 1 divided by determinant of A adjoint A, and then similarly let's take A out there. So we'll get 1 divided by determinant of A adjoint A. So we are taking this A outside, which is equal to I. So you can see that this equation and this equation are similar. Both have A into some element, and then A into some matrix, and some matrix into A is equal to I. So here to A into some matrix and matrix into A is equal to I. So here we have some similar elements. These both are somewhat similar, right? But in the place of A inverse we have this term. So that what we can write, A inverse will be equal to, which means this A inverse will be equal to this term, which is 1 divided by determinant of A adjoint of A. So this is how we found the formula for A inverse. Can you understand? If we have taken this element from here, which is these both equations are similar, but only difference is A inverse. In the place of A inverse we have this term. So what we can write, this A inverse is equal to this term, which is A inverse is equal to 1 divided by determinant of A into adjoint of A. So therefore you can write determinant of A inverse exists. So A inverse exists. You can see here, right? So A inverse exists, and it is given by, A inverse is equal to 1 divided by determinant of A into adjoint of A. So this is the formula for A inverse. Now let's see some amazing fact. The world record for folding a piece of paper in half is only 12 times. There is an old myth that you can't fold a single sheet of paper in half more than 7 times because each time you make a fold, the thickness of the paper doubles and requires impossible amount of energy to finish it. But thanks to an American high school student, Brittany Gallivan, so that we now know that paper can be folded more than 7 times, but not much more. Gallivan currently holds the world record for paper folding at 12 folds in a single sheet of toilet paper. Thank you guys. Thank you so much for watching. I hope you are clear with this now. இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்தா லைக் பண்ணுங்கள், கமெண்ட் பண்ணுங்கள் அண்ட் ஷேர் பண்ணுங்கள். அண்ட் நீங்கள் இன்னும் என் சேனலை சப்ஸ்கிரைப் பண்ணலன்னா மறக்காமல் சப்ஸ்கிரைப் பண்ணிவிடுங்க. See you in the next video. Bye.